Anyone response in chat box? Please put S in chat box if my voice is clear means. So good evening, Sri Krishna Electronics. So Chaudhary, good evening. So Raghuram, good evening. So thank you for joining. Thank you for your presence in this session. So today is the 13th. So yesterday we have some technical issues, so that's why we didn't go live yesterday. So today we're gonna see counters. So can anyone respond in chat box? That's why I can verify. I can ensure I'm clear. Just if my voice is clear, can anyone put S in chat box? I'm audible to you. Okay, no problem. Thank you, Pranav, for your clarification. So let's wait for a few minutes, 1 or 2 minutes. How many people have to join? So let's wait for a few minutes. So good evening, Pranav. So good evening to all. Yeah, welcome. So today we're gonna see counters. So counter is a main important topic in Verilog. So it is used in frequency divider. If it is used in like a real-time scenarios, we are using counters everywhere. So counter is a very important thing in a digital design. So some block need delay, some signal need much delay or much more delay, or some signal need less delay. For delay perspective, we have to use counters. So counters are a very important thing. So in this session we are going to see that only. So there are two classification of counters like asynchronous, synchronous, up counter, down counter, like that. So today we're gonna see that. So let's start the session. Thank you for joining. Thank you for presence here. So counter. We know that counter is mainly using for counting purpose. It will start from 0 to 50. It is means up counting. So it will do down counting means 15 to 0, 15, 14. So this up counting and decounting. We'll try to write the code in Verilog in this session. Up counter, decounter, and then both up and decounter and up and down counter in the same Verilog code by using the mode signal. So we based on the mode, it will go up counting or it will go down counting. So let's see the what is counter. See, a counter counts the number of times specific event has been occurred. So it means we know that counter for counting purpose in the digital design we need to use some triggering element. So some triggering signal or triggering event only. Based on that event only it will do counting. So for that for counting purpose we must have to use sequential logic like a flip-flops. So we know that flip-flops fully based on clock only. So it will perform, it will receive and store data, and it will give output based on the clock pulses. So it may be negative edge, it may be a positive edge. Based on the clock pulses only it will operate like a sequential circuits. Same like this. So same like sequential circuits. If you want to do counting means, or if you want to do build a counter means, you must use the clock signal. So from the clock signal, every passage of clock it will do counting. So for example, if you do counting means at first passage, like in the clock first passage, it's like a positive clock edge. It will count 0 to 1. In the next clock cycle positive edge, it will count 1 to 0. It will increase. It will increase based on the clock pulses, like a clock edges. If using the clock positive edge, it will count based on that particular positive edge. If you are using the negative edge in your code, it will it will count the based on the negative edge in your clock. So clock is very important thing. So clock is a very plays vital role in the counters. And also counters also are mostly used in the clock frequency division. So if you have in the 50 megahertz clock, you have to divide the clock. So my input clock is 50 megahertz, but you need only 25 megahertz. For that purpose, for that scenario also, we can use the counters. So mostly we use the PLL, like in the, if using in the tool. So in the, if you take an Xilinx or a Vivid Altera, there is a PLL block. So by using PLL, the tool will create the, or tool will write the RTL code for frequency divider. So if you want to manually do, means you have to use the counters. So based on the counter, you can do the frequency divider operations, like increasing the clock frequency, decrease the clock frequency, like a 50 megahertz to 20 or 50 megahertz to 100. By using that particular counter, we can achieve that. So let's see that kind of clock division in upcoming sessions, while implementing the FPGA, like LED blinking or sound segment. We must use counters, then only we can give delay. So on that time we will see the how counter will work in the clock frequency division. So today we are going to see only counters, how it works. So same like this, today we will see some logic. Same logical we'll apply to in the upcoming classes, while implementing the FPGA code. So today we are going to see only simple counter, like a up counter, down counter, and then up down counter. So let's see the block diagram of the counter. So if you are using the 4-bit, means you can count up to 15, like a 16 only. Why? Because of, so 4-bit, if you imagine 4-bit, if all bit 1 means 1 1 1 1, it is refers to 15, so 0 to 15. And then if you are using a 5-bit, means it will count up to 32. If you are using the 6-bit, means it will count up to 64. If you are using the 7-bit, like a range of the counter, so 4-bit counter, 5-bit counter, 6-bit counter, the range of the count based on the bit only we can count that much level. So if you're using the 7-bit, means you can count up to 128, like that. So this is the block diagram for the counter. So n-bit binary counter. So it will start from 0 and then it will go to 2 power n minus 1. If the n is 4, means 2 power 4 8, like 2 power 4 4 4s are 16, minus 1 15. So you have the 15 counts, like 0 to 15 counts. If you are having the 5-bit counter, so n equal to 5, 2 power 5, so you will get the 32. So 32 minus 1, 31, it will count 0 to 31. So this is the block diagram of the counter. So we know that two types of counters, up counter, down counter. Up means it will increment from, it will start from 0 to 0 1 2 3, like that. Down counter means it will start from limit, like if you are using the 4-bit, means it will start from 15 14 13, it will decrement. So up means increment, down means decrement in the counter. And then this is the main thing, asynchronous counter and then synchronous counter. So we know that name itself having the asynchronous. So for counting operation, so if you want to counting operation, means you just need a flip-flops and the clock inputs. So if you 4-bit, means you have the 4-bit 4 flip-flops. By using the 4 flip-flops only, we are doing 4-bit counters. If you are doing 5-bit counter, means you need the 5-bit 5 flip-flops and then 1 clock input. So if you take any asynchronous counter, it will use the clock, but the first flip-flop only it will use the clock. Remaining 4, if you take in a 4-bit, means you have the 4 flip-flops. So I will show in the diagram. So it is a example for the 4-bit asynchronous counter. So I am having the 4 flip-flops. You can see here the first flip-flop only it will take input from the oscillator, or it will take the global input for clock. for the second flip-flop, it is depends on previous flip-flop only. So based on the output of previous flip-flop, it will given to the second flip-flop input. Same here, this flip-flop is depends on previous flip-flop. Based on the previous flip-flop only, it will given to the input of next flip-flop. So this is asynchronous. So each and every there is a first flip-flop only. It will receive the global input clock or clock input from the oscillator, but remaining flip-flops depends on previous flip-flop output. So this is asynchronous counter. So you can see also here in the asynchronous counter we don't use universal clock. Only first flip-flop is driven by main clock, and the clock input of rest of the following flip-flop is driven by output of previous flip-flops. So it means only the first flip-flop will use the global clock. Remaining flip-flops are performed by the previous flip-flop outputs. So this is a asynchronous counter. So by using this asynchronous counter means there is a one disadvantage, like here if you want to do second bit, if you want to perform this flip-flop means you have to wait for previous flip-flop output. And also if you want to get if you want output from this flip-flop means you have to wait for these three flip-flops must be compute, and it will give output. So based on these three previous flip-flops output only you can get output. So there is a delay, so there is the time taken, so there is a time taken to give output. So it is very slow counting operation if you are using the asynchronous clock. And also it's like a ripple clock, like a ripple carry adder. So every full adder output, like a C out, will be assigned to the next full adder, same like that. So in the output of the each flip-flop will be assigned to the input of clock in the next flip-flop. So this is the main thing. So each and every if you following this like asynchronous counter, your counter will be very slow compared to this synchronous counter. Why means, so if you do, you can see in the synchronous counter. So this is example diagram of a block diagram of synchronous counter. So each and every flip-flops will connect the clock by separately. So this is a clock oscillator. So you can see each and every flip-flop will pass clock separately. So the signal is this is a clock line. It is assigned to this flip-flop, and it is assigned to this flip-flop, third flip-flop, fourth flip-flop. Each and every flip-flop assigned separately as a clock input. So it will do parallelly. So it will perform parallelly. It will do like a counting very fast. So it is faster than asynchronous clock. So asynchronous flip-flop, like a counter. So there is a difference between the asynchronous and synchronous. Asynchronous means mainly it is depends on previous state or previous flip-flop output, but in synchronous we don't have that scenario. We having the separate input. So separate input for each and every flip-flop. So this is the synchronous clock. So synchronous counter. So you can also see here synchronous counter has one global clock which drives the each flip-flop. So output changes in parallel. The one advantage of a synchronous counter over the asynchronous counter is that it can operate the higher frequency. So you can see higher frequency than the asynchronous counter. And as it does not have any cumulative delay because of the same clock, so there is no, and also there is also no delay here. So why? Because of they are parallelly operating, so there is no delay for clock assigning. It won't wait for previous flip-flop complete. So there is no delay here compared to the asynchronous counter. So this is a fast counting and then high speed counter, synchronous counter. So this is the difference between them. Let's see the application of the counter. So we know that a complete counter may fully counter is used for counting and also useful for time measurements. So for example, if you take any traffic light signals, if you can notice that also, like it will take some time, like 15 seconds or 5 seconds to change orange to green, or red to orange, or green to red. So it will take some seconds. For that, maybe it will do up counting, mostly traffic lights are doing the down counting, like a down counter. It will reducing, it will do decrementing, like 15 to 0 or 5 to 0. So based on that, counters are used in time measurement, and then analog to digital converter, and also if counters are used in frequency division. So I already said, no, if you want to increase the frequency based on from like example, if you are having the 50 megahertz of clock input, if you have to increase, means you can use a counter for that. So it will do counting based on our required frequency. So there is one formula. So if you want to if you want to certain output, means it's like a output frequency by input frequency. Output frequency means 100 megahertz. My current input frequency is 50 megahertz. Like there is a formula. So we'll see in the upcoming sessions how counters work in the frequency division. So these are the applications of the counters. So and then let's move to guys, if you guys are really interested in the 21-day masterclass on YouTube, you can convert in this masterclass into 1 month internship on FEJ. So these are the things you will get as benefits. So benefits are 30 days recording session, all 30 days presentation, exclusive project codes, VIP community group. It's for your doubt clearing on the internship updates. So you will get the IT internship confirmation letter. So and then you will get the 90 days LMS course access. So and then assignment and task, weekly live sessions, resume building, mock tests. So these are the things you will get as benefits of internship, and also you will get an internship certificate and also participation certificate. So these are things, these are benefits. You will get at a discounted fee of 999. So if you guys are really interested, you will get at 999. So regular fee is 3,999, like 3,999. So by using this registration link, you can register for internship, and also you can use a link in chat box. We will post my organization will post a link in chat box. You can access that. So this limited time period offer, so it will end at 28 March. So if you guys are really interested, you can join our internship program. So let's move to the coding part. So we'll try to the writing RTL code for up counter, down counter, and then up down counter. So firstly, module my module name is counter. So firstly I'm gonna write up counter in module. So my input and output signals are, so if you want to write the code in counter, means my inputs is clock is my first input, and then reset is my second input, and then this is my input signals. My output is counting output is counter. So this is my output. So and then I'm gonna write the code for 4-bit counter. Gonna write for 4-bit counter. So for that I'm using here range 3 down to 0. Okay, it will count up to 50. So and then I'm gonna use another register variable, like so it is also store, it can store up to 4-bit counter register. Why I'm using register means if I use I'm gonna use always block. So if I'm using the output in the always block, I'm gonna write here edge, and also if I using my output in the always block, sometimes I will may receive the unknown state as output or high impedance output. So there is a confusion or there is a conflict in the always block while writing the code. So for that I'm using the register here. So I'm for register here. Let's see how I'm using the register for writing the counter. Always at passage of clock. So passage means past edge of the clock or negative edge of the clock. If any positive edge or negative edge are triggered or means negative edge of reset. So if anything is triggered means it will do executing. So you can see here I'm doing OR operation here. If any one of from positive edge of clock or negative edge of reset, anyone is triggered or changed means it will start executing the always block. So this is my always block. So I'm just return my input output signal and then register and then always block. So and then I'm gonna write the logic. So if firstly I'm gonna write logic for my counter in the reset condition. If my counter in the reset condition means I'm just writing my counter register equal to 4 bit of decimal 0. So and then else if it is not in reset condition means it will do up counting. So in the reset condition I'm assigning my logic you must stay in the 0. So you in the reset condition you having the 0 only. So same like that, if it is not in reset condition means it will do up counting. So for that counter reg equal to, so counter reg plus 1 bit decimal 1. So it will increment. So firstly it will stay in the reset condition, it will stay in the it will have the 0 value. If it is not in reset condition, previously I am assigning 0 here, 0 plus 1. So it will assign to this variable, it will have 1, and then already in the next clock cycle it having 1 here, 1 plus 1 2, here you have 2, and then 2 comes here, 2 plus 1 3, and then 4 comes here, and then 4 plus 1 5. So it will do counting like that. So this is a counting operation. And then I'm gonna assign here, this is a continuous assignment. So my output signal is counter. So in the continuous assignment we can't use the non-blocking, we can use only blocking assignment. So and then my counter, this counter register only, it having the output values. So just use a counter reg. So I'm gonna write the test bench for my design code. So just okay, so this is my design code. I just save and run to check my error. So I didn't get any error, so let's move to, I have an error here, undefined variable counter. I just mistake here in the 18th line, COUNTR, just made mistake here. So just run again. so zero error. So and then I will move to write a test bench code for my design code module, test bench, and then my end module. So and then I'll move to my, so just stop, it's running. So here register clock, and then reset. So these are my inputs. My outputs I have to write in wire. So 3 down to 0 counter, counter. So and then I have to instance state my design code and test bench code. For that I'm gonna use port by names, so like a port by order. So there is a method of instance staging. So my firstly up counter, and then my instance name is A1. So and then I'm gonna write my signals. I'm just writing my signal like a clock, reset, and then counter. So this is a method of port by orders. So order means, so signal order. So in the module, first signal is clock, second signal is reset, third signal is counter. So in this test bench instance staging, you can also use by order methods. Like if I am using here clock, so this clock, so this I'm it means it will directly connect the signals by order. So clock, reset, counter. So if I run this, I will check. I run this, I didn't get any error. So this is mapping. So mapping by order. So if I change here, if I change reset in the clock, let's check how it works. Even though I didn't get any error, but while passing the signals, it will change. Like my reset signal will be assigned to the my clock signal, or my clock my reset stimulus will assign to the reset. There is a chance to mismatching the values like a stimulus. So for that we have to use correct ordering like a clock, reset, counter. So and then I have to create my clock. So my clock is always at every 5 nanoseconds. My clock will be toggling. So at every 5 nanoseconds it will toggle. So and then, so I just created my clock, and then I'm gonna write a stimulus. In the stimulus, firstly I'm just write my dollar monitor to see my output values. I want to see counter value only. Counter in the form of decimal. So and then counter here, and then so in the starting, in this initial stage of my simulation, my reset will be high, and then after some delay I given reset equal to 0. So I will run up to 200 nanosecond. So this is my test bench. So this is my test bench. So I just and then I want to give clock value, clock equal to 0. So at my initial stage of simulation, I am passing stimulus for my design code is reset equal to 1. So it means in the initial stage of simulation, my design will be in the reset condition, and then I'm also my clock, I'm passing stimulus for my clock equals 0, and then after my 10 nanosecond I will just reset equals 0. It means I just off my reset condition, so it will work this counting operation. So let's check. So I made mistake here. While I want to finish my stimulation, while I am using only the clock, so I want to finish my stimulation, then only it will complete the simulation. Otherwise it will work, it will execute up to the clock simulation. So clock will be never stop. Why? Because of it will continuously toggling. So we want to stop the simulation. For that I am using $finish. So and you can see here, initially it having unknown value in the reset condition. After that it will start counting, up counting from 0, 0, 1, 2, 3, 4, 5, 6 up to 15. So it will do up to up counting up to 15. Why? Because of it will do the range of counter is bit range of counter is 4 bit only. So there is a 4 bit of counter. So this is the thing. So if you want to do down counter, means just simple thing only, TOW1. I just change here. It will start from 15. So 4 bit hexadecimal of F, it means 4FF, it means 111. And I want incrementing, so I just change my sign here, minus, to do the decrement, like a down count decrement operation. So I just run this. I want to change here also down. So I just change here. So line 12. So line 12. So currently I am doing the down counter. So for 4 bit it will my last, if I'm using the 4 bit counter, so my final count is FF, like F15 only. So for representing the 15, I'm using the hexadecimal form. 4 tick hexadecimal FF means F means like this only. I can also use like this binary 111 1. You can also use this. So I just run this. So and you can see, and you can see here it will do decrementing. So it in the initial stage it having x unknown value, and then 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 2, 3, 1. So it will do 2, 3, 1, 0. It will do decrementing or down counting, up counting. This is the code for up counting, down counting. So I just change here minus symbol. It will count, and it will decount by 1 bit. If I change like a 5 means, let's check how it works. It will decount by 5 bits. 5 count. Sorry, counts, not a bits. So why it will change 1 bit decimal 5. So 4 bit decimal 5. Yeah, you can see here 15, 10, 15, 10, 5, 0, and then 11, 6. It will do some negative operations also. Why? Because of its unsigned nature. Basically my input, if you writing input means this my signal, I am writing input only. it will take data type basically by default wire. Wire is the default data type of my input signals. For these signals, I didn't give you any data type for the signals. By default it will take wire. So wire is a unsigned in nature. It will do some counting. Wire is unsigned in nature, so it is unsigned means it will only having the positive value. In the decounting it will give some this value like this only. So 10, 15, 10, 5, 0, and then 11, 6, 1. So it will do something. So I just change here 4-bit decimal 1. So this is up counting and down counting. So let's try in the both up counting and down counting in single code. So I just add up and down, and just add on another signal mode. So 4-bit of 0. So in the reset condition, my clock counter edge it having the 4-bit of 0, and else if mode is high. So mode is high means it will do up counting. It will do up counting. So if mode is high, it will do up counting means I have to change here equal to 1. If mode is 0, else if it is 0 means it will do down counting. So counter edge equal to edge. For down counting, counter or edge minus minus 4-bit of root of binary 1 1. So let's check up and firstly here I'm given like a mode equal to 1 to do the up counting. Let's check. So and then I have to change here up, and then in the module also like a mode, and then here also I want to use mode. So I just run this. Testbench 16. So I just made semicolon mistake here. Save and run. Testbench 15. Where is 15? You can see it will do the up counting from 0, 1, 2, 3, 4, 5, 6 and up to 15, and again it will start from 0. So let's check the down counting. If mode equal to 0 means, so I'll change mode equal to 0. It will execute this down counting. Let's check. So line number 12, counter spelling wrong. Testbench. So inside the bracket you can write anything. So here you can write anything. So you can also write a pantech. It is just for printing. So inside the bracket we can write anything. And this percentage, this modulo t is refers to this particular signal, which form you want, like in the binary number form, or in the decimal, or in hexadecimal. So that is a string. So this is important. So if using this, it will directly like indicating this. So it is referring this. If I use another signal, like if I am using another clock, I'm using another signal clock, and then I just write modulo d. It is this this refers to this signal, and then this modulo d or a percentage d is refers to this clock, though this same signal. So let's check how it's get. So you can see here I'm doing the upcounting. So this is my counter value. This 0 and 1, 0, 1, 0, 1, 0, 1 is refers to clock. So I'm adding my clock here. You can notice I just add the clock here after my counter value. After that only my pantech. So you can see here the pantech will I'm just written. So firstly it will do this, and then it will print this, then it will print this. So this inside the double quotes you can write anything, so it won't give any error. But while writing the here we have to give correct like a correct spelling for the signals. So I just made, so it will do upcounting. So this is a way of writing up counting and down counting. So counter is very important thing in the digital design. So while in frequency divider or timer. So this is for today. So already in this session we seen like a counter, synchronous and asynchronous, up counter and down counter. So in the upcoming session we'll try to use counter in our code while implementing FEJ, while LED blinking. So even though LED blinking, you may maybe think like LED blinking is a simple thing, it is not like that. So for LED blinking we have to give delay. So for 1 second, 2 second delay, for that we have to use count, then only we can give the delay for the LED. So it is important basic thing. So in the upcoming session we'll try to implement counter and also implement in FEJ. So thank you guys, thank you for listening. This is for today. So video broken, so sorry for that. So I think hereafter we'll give the correct content, clear content without any disturbance. So thank you for listening, thank you for joining. We'll see you tomorrow with new topic. Thank you.